Before, yeah, okay. Before, you need to explain this question to me, and then you can after that you can code it up. You can start coding, and then you need to explain the time complexity of your solution and the space complexity. You also need to say, okay, you can start it now.
Okay, today we're going to solve trapping rainwater. This is a very famous question, most likely given in the Goldman Sachs CoderPad round, disguised as the snowpack problem. So we're going to solve this question using a two-pointer technique, but first let's read the question. So we have a number of non-negative integers, which means greater 0 or greater, representing an elevation map where the width of each bar is 1. So each unit of water is 1. And we want to compute the maximum amount of units of water we can trap after raining. So the way we're going to do this is we're simply going to start at the ends of the array, and we're going to move inwards based on which height is less. We're going to move that pointer in because we want to minimize the number of restrictions as we want to find the maximum amount. So I'm going to draw a picture here. So in this case, for example, we're going to move left pointer in because left is less than right. If they're equal, then we can move either pointer, let's just say right in this case.
Okay.
And at each iteration, we are going to find how much water we could trap, if we can trap any water at all. So the way we're going to determine that is because the blue squares are what we can trap. And yeah, so the way this works is we are going to subtract from the outside compared to the inside. So for example, here, 0 is less than 1. So we cannot trap any water. But by the time left gets to 0, which, excuse me, my next iteration, this is going to happen. So in this iteration, 1 is bigger than 0. So what does that mean? That means we can trap 1 unit of water. So then the maximum amount of water we can trap up to this point coming inwards from the left side is 1 unit of water. And we're going to keep a variable and update that. But the values and the way the pointers move are going to be compared by the array values from the input. So because 0 is still less than 2, we're going to move inwards again. They're equal now, so we can move either one. Let's just say right, make it simple. So now right is less than left, so we're going to move right inwards. 1, 2, 3, let me just make sure this is correct. Okay. Yep, so now they're the same. Move right. But as we're moving, what we want to do is compare the outside. So for example, we can't trap any water here because, first of all, we're on the edge of the boundary, so we can't ever trap any water at the first and the last values of the array. We can't trap any water here because 1 is less than 2. But now when we're going inwards, 1 is less than 2. So the outside has to be bigger than the pointer we're currently on. The pointer we're coming from has to be bigger than the pointer we're currently on. And then now we can say we can trap 1 unit of water here from right. And at the end, we're going to keep moving inwards. And at the end, we're going to have a result because every iteration we compare a unit of water we can trap, we're going to have a result variable that basically sums up the entire units of water. So we're not going to add left and right pointers at all. So right now, 2 and 2, we're going to move right as we agreed. So now 1 is less than 3, or 2 is less than 3, sorry. So we're going to move left inwards. And now notice we can trap another unit of water from left because 2 minus 1 is 1. And then because 1 is less, so now we're going to move left pointer in again. And so now we have 0 and 3. 0 is less than 3. So now left is on 1, right is on 3. 1 is less than 3, but this is an important part because we cannot, as you can see from the diagram, we can't trap any water at the highest elevation.
Yeah.
So these pointers cannot cross. As soon as they do cross, they step over each other, then we're going to break out of our while loop and we're going to return a result. Valid condition. Base case, but this is not recursion, but you get the point. And yeah, so that's how it works. The time complexity of this, I believe, is O of n because we are traversing every element in the array from the outside to the inside one time, depending on the size of the input. So if the input has n elements, then the time complexity is O of n. And the space complexity is O of 1 because we are just using a result variable to store the number, the amount of units of water we can trap so far and returning that at the end. So there's no extra memory used.
So you say the space complexity is B of n, right?
It's constant because we're not using any extra memory.
Yeah.
There's no linear amount of memory. Just because the input size grows doesn't mean that we still have one variable that we're going to return at the end. We're not storing anything else.
Yeah. Okay. I think you can code it up.
Okay. So first, let's define our pointers. As we agreed, one is going to start at the beginning of the array, and one's going to start at the end of the array. But before we do that, we're going to take care of our base case. So if the input array is empty, then we can return 0 because, again, the instructions say n non-negative integers. So that means 0 or greater integers. Okay, so now that we have our pointers, now we can declare this condition where left has to be less than right. And so first, before we do that, we're going to keep track of the maximum water we can trap from either side. So let's call this max left and call this max right. And at the beginning, it's going to be the value that we see. So again, 0 for max left, 1 for max right. And while our pointers haven't crossed, we're still in bounds. So we're going to ask if max left is less than max right? Because whichever one is smaller, we're going to move inwards because we want to eliminate the number of restrictions because we want to find the maximum amount of water we can trap. So if max left is less than max right, then we can move the left pointer inwards. And then this is the key part where if we're going to find the max of height of left because we moved inwards. So height of left is 0 now. And max left, the one we came from is going to be max left, right? Because it was 1 previously. So if max left is bigger than height of left, then we can actually trap water. So we're going to have a result variable here, max left minus height of left. Because if max left is a bigger one, we still want to subtract by the older one. So in every other case, if they're equal, then we can move the right pointer inwards. And we're going to do the same here. We're going to find the maximum of the current versus the previous. Height of right, max right. And we're going to add that to result, max right minus height of right. And at the end, we can just return our result once left and right pointers have overstepped, and that should be it. So let me run this.
Okay, nice. Oh, okay.
Submit it now. Yeah, that's it.
Okay.
That's trapping rainwater.
Yeah, thank you for explanation this question. So I will start recording now.